that solution. And so when using those methods, you have to be careful to minimize the effect of round of errors. And so the other methods you looked at, the inverse methods, the Cramer's rule, those one you looked at them at some other level. So here we focused on first the Gaussian elimination method, where a system AX is equal to B is reduced to triangular system, and then you solve by back substitution. So we say that one way of improving the solution is, since these methods are sensitive to round of errors, to reduce the errors, we can apply what is called the pivoting. So you look for elements with the largest magnitude, and then you make it the pivot element. So along the pivot row. So that's partial pivoting. With full pivoting, you scan through the whole system and identify element with the largest magnitude and make it pivot element. So those were just to minimize round of errors. And then we can pick from there and then just do one example to illustrate the full pivoting. Partial pivoting mostly is just switching the equations, so nothing changes about the solutions. But with full pivoting, what happens is you switch, whenever you switch columns, then you have to keep track of your variables. And so I wrote here some matrix. I don't know. Can somebody, did you write down the examples? Can somebody give us an example we can try with partial or full pivoting? So among the examples you wrote down, can somebody give us an example? So I just want to do one example to illustrate the full pivoting. I saw the partial pivoting is, so if you know full pivoting, then you know partial pivoting. So I'm just doing full pivoting because in full pivoting, you have to keep track of your variables, how they change positions. So any example from you? Yeah. 2.11. Which are the variables? So this is x1, right? Yeah. Then minus 4 point x2. 921 x3. Is the same as 2.01. The second equation, 4.01 x1, 10.2 x2, 1, 2, x3, the same as 3.09. Then the third equation, 1.09 x1, x2, x3 is the same as 4.21. Okay. So given this is our system, maybe I just do 2 steps and then you can complete. So we just want to track of what happens. I said the first step is we write down the augmented matrix. So once you have done this, let me comment. Once you have done this and then you have understood what happens, you can even switch this before coming up with the matrix. You can switch the equations and variables as you want. And so as I said before, some of these steps can be combined. You can even do multiple steps at a go if you understand what we are doing. But if not, just do it systematically, step by step. So if you extract the augmented matrix, so I'll have 211 minus 4.21 and then 0.921, and then you augment our system. So that's 2.01. The next is 4.01, 10.2, and then I have 1.12, that's negative, minus 3.09. Then lastly is 1.09, 0. And then 0.832, 4.21. And so when you do Gaussian elimination with fully pivoting, since we want to keep track of the variables, then you can just put variables on top just to, so it helps so that you know that when you switch columns, you are also switching the variables. So for example, if I switch column 3 and column 2, then to me the x3 and not x2. So that's why most people confuse that when they are doing full pivoting, they will solve correct solutions, but you are assigning them to the wrong variable. And so we said if we were to use the partial pivoting, then you only scan the pivot row and identify the element with the largest magnitude, which would have been 4.01, and then you switch. But so if you do the full pivoting, we identify elements with the largest magnitude in the whole matrix except the solution part. So in this other, the matrix part, which in our case is 10.02. That's the element with or a number with the largest magnitude. So the task is to switch this number and make it our pivot element. Basically, I want to bring 10.02 to where there is 2.11. So I want to bring this number here. So can somebody tell me the operation I'll perform such that 10.2 is at the position of 2.11? What do I do?
You can set.
I think you'll switch row 1 and row 2, then column 2 and column 1.
Correct. So that will work, but that's not the only way, but that also will work. So, and that one will have done 2 steps at a go. If you are not sure, since you want 10.22 at the first position, then you can switch column first, you do the first step, and then switch rows. Or you switch rows, and then that becomes the first step, and then you come back the second, and then you switch the columns. If you know, then you can do the 2 steps as you have mentioned at a go or simultaneously. So if we do the 2 steps, what have we said? That we are basically switching row 1 and row 2, and then we switch column 1 and column 2. So that's what we said. And so this now where this becomes important. Remember, when we switch column 1 and column 2, what happens? What have we switched in terms of the variables? So if we switch column 1 and column 2, anytime you switch column, you are also changing the positions of your variables. So when you switch column 1 and column 2, it means now the elements here will correspond to x2, and elements here will correspond to x1 and x3. Nothing happened to x3. So when you solve this, it means your first solution will be for x3, the second will be for x1, and then the third one will be for x2, and not x1. So they will have switched positions. If you don't keep track of this, how these ones are moving in full pivoting, then you lose the sense. You will get the right solutions, but you will assign them to the wrong variables. And so if we switch this, so here I'll have 10.2, right? And then I'll have 4.01, and then minus 1.12, and then I have minus 3.09. If I make a mistake, you let me know. And then here, I'll have, because we switched row 1 and row 2, and then we switched columns. So here I'll have minus 4. I'll have 2.11, and then I'll have 0.921, and then I have here 2.01. And then what happened on the third row is only the switching of columns. So I have here 1.09, and then 0.832, and 0.41. So who does not understand what we did? So silence means okay. So once we have moved, the largest element is our pivot element, and then we can now define our multipliers. And so since you have done this, you can do your, if there are so many decimals, you can do your answers to maybe to 4 significant figures. It's okay. So I can say that mid multiplier 21 is the same as minus 4.21, so it will be plus divided by 10.2. Tell me what that is. And then multiplier 31 will be minus 0.987 divided by 10.2. Remember what we said is negative A21 over A11, negative. So give me these values. This in your calculator. The first one, what is it about? 0.4127. And then this other one, 676. So that is 67. Yes, 676. So 68, right? And then so now we know that, so when we reduce, row 1 has not changed.
Excuse me, sir.
Yeah.
The multiplier 31 should have a negative.
Yeah. I'll put a negative. Thank you. Yeah. So the first row, nothing changed. So if we reduce, this will be 0, this will be 0. Because remember, so this is just row 1. This will be what? This will be lambda 21, row 1, and then plus row 2. And then this will be lambda 31, row 1, and then plus row 3. So just multiply by the first row or the pivot row, and then you add to the second one. And so if you reduce, this will be 0. The second value, this is 4.01. What is this? What are these values? Can you tell me what are these values? Then this is 1.12, and then here I have negative 3.09. You are just taking the multiplier, multiply by 4.01, and then add 2.11. Then but you can do this in the calculators. Just quick. So as one is doing this, others can do the others, and then you give us these values. And that's how we can move faster. You guys don't have calculators, or don't know how to use calculators. Minute to do what? No, you just give me one by one. If one of the numbers you want to spend a minute, it means if you want to do 5. Mm-hmm. 3.76. Uh-huh. 0.0018. Oh, here. So this is 0.7018. Uh-huh. These guys are not calculating, then I will not do the examples. I will just explain, then you can do the rest at home. We cannot sit just wait for people to do the just use calculators, things you can do within seconds. So but you are the only one speaking. Where are these other guys? So that is Ismail is the only one saying something. I want everybody to participate.
Column 3, row 2, 0.459.
0.459. And then here.
9.
And also people should also do the others.
And then column 3, row 3 for me, it's 0.743.
743.
Yeah, but column 2, row 3, I'm getting 0.886.
Which one?
The one
this?
That's written 0.7018.
The others, what are you getting?
But let me just confirm.
Yeah, also others can confirm. You know, if all of you will do this, and then we can we know where we are making mistakes. But it is funny that people. Somebody has put something in the chat. Row 3, column 2. That's 0.7019. That's row 3, column 2. So another one is getting 0.7019. Another one is 0.7018. So those ones are just almost similar. So the effect of round of error. So you should make sure that you get the correct rounding of errors. This round of. So 709 and 708, to me, they are the same. It's just one of you has not rounded off correctly, or one of you used the full digits. And these other parts, this. Now, first, let us start from multiplier. Are all your multipliers correct? Okay. So if the multipliers are correct, then why are we getting these different values? It's surprising to me.
Yeah, it should be 0.9404.
So are the other, if you check the first column, are the other numbers correct?
Yeah, the others are correct.
So where is the mistake? So this last one is so the last one is 0.0968 multiplied by 4.01. And then we subtract what? Minus 1.09, but it becomes positive. This is 0.18. This is correct. So the others can check what you got. So to me, I'm also getting this. And then the other number is what? So the other number is 1.12 multiplied by 0.0968. I did something wrong. 1.12 multiplied by
excuse me.
Yeah.
Yeah, for the bottom row, I did very wrong stuff. Yeah, so
it's 1.916, right?
Let me just redo it, but I did something wrong.
Can somebody confirm this? Is it 1.9?
No,
1?
it is 0.94.
Oh, I also made a mistake.
Yeah, you didn't take the negative 1.12, you took as a positive.
This negative and negative.
Yes.
Yeah. So when you multiply this, this becomes a
positive, but at the other one you subtract.
Why do you subtract and you are adding to 0.832? Huh?
I did that one, the multiplier negative 0.0968 multiplied by negative 1.12. Then you
get
add
a
0.
What do you get? First, you just multiply those ones. 1.12 multiplied by 0.968. What do you get?
Let me see. I did it the whole.
And then plus 0.832. I'm still getting 1.9162. Can you confirm your values? I might also make a mistake, but can you confirm what you did? Because it's 91616. So I told you that when you do full pivoting, just keep track of your variables. Can you confirm that what I did is correct?
The answer is 0.9404.
Yeah?
What you did is wrong.
Let us go step by step. What is 1.12? You multiply by 0. Okay. 0. Okay. I think I was multiplying by 0.968 instead of 0.0968. Okay. Yeah, you are right. I was multiplying by 0.968 instead of 0.0. Yeah. And then plus 0.832. 832. Yeah, you are correct. So you get
0.9404.
0.9404.
04.
Yeah, correct. And these are the variables. And so this is what I mentioned to you about numerical. That some of these things you may know the procedure, but you start making these mistakes. And so if you don't practice, then you are in trouble. If you wait to practice in the exam, you will know what you are doing, but you make this kind of what looks simple errors, but they cost you marks. So give me these other values. 0.7, 348, and then 91. And so having that's the first step is done. We now go to, let me remove the highlight here in this other so that yeah. Then we go to the remaining smaller matrix because we are finished with row 1. So you don't, when you check the largest magnitude, you don't check row 1. Now we only check the remaining rows. So if you check these remaining rows and columns, what do we notice? We notice that, so this, now here there's no any change we make, right? 3.7649 becomes our largest magnitude. So that's directly our pivot, nothing, we are not changing anything. And so we define now our new multipliers. We define lambda 23 as, it will be minus 0.7018, then divided by 3.7649. What do we get?
Negative 0.186.
Negative 0.1863. And so we do the same. Nothing changes on row 1. So row 1, nothing changes. So it is 10, 0, 0. Row 2 is 4.01. That is 3.7649. And then we have here 0. So that one you don't even have to do it. Just know it will be 0. Last, this is 1.12. Give me these values. 0.459. What is this value here? And then I have here negative 3.09. And then I have 0.7348. I need these last two values.
Zero point 8549.
0.8549. And this? But I'm surprised. This class has so many people. But people are just quiet. Ama wengine mko class mmelala.
Four point 372.
4.372. 4.3772. And so now we have already reduced our system into echelon form. If you look at this, since this is not a zero row, our system has solutions. I said that if you have a zero here and there's a number, no solution. If you have a zero here and you have a zero here, many solutions, which I gave you in the assignment that you have to go and make a program. And remember, just do the program. I will collect those assignments. I will ask you to submit. So you keep making the program. You keep, if we come up with something else, you keep developing that program, and then we will correct at some point. So if we are here now, we can now solve by back substitution by saying that now x3 is the same as 4.372 divided by 0.8549. So you can give us those values. That gives us x3.
5.11.
5.11. And then now we can solve for x1 now. So it means 3.7649 x1 and then plus 0.459 x3 is the same as what? 0.7348. You don't even need to extract this line. You can just go directly and then you solve. That means my x1 is the same as 0.7348 minus 0.459 multiplied by x3 is 5.11 and then divided by 3.7649. Give me those values. So you see, this is where now people confuse. If you didn't track the variable, you will get the correct solution here, but yours will be x2. So you will be corresponding to x2. So you have the correct solution, but assigned to the wrong variable. That's why I said in the full pivoting, you have to keep track of your variables, how they are changing. And the variables switch positions only when you switch columns. So somebody says, but can you try to put your answers to 4 significant figures where possible? Instead of, I'm just saying you are writing it to 4.2, unless it's terminating decimal. If not, put to 4 significant figures. Minus 4.90, and that is getting minus 4.28, and that is 4.4278. Why the difference in answers? 429. Oh. Now we have two different solutions. Which one is correct? 4278. 4278. Let me assume minus 0.4278. But you can just try this. Make sure that always do practice this thing so that you don't make mistakes. Just do practice. That's the only thing I can tell you. Because you will know the procedure, but you may get the wrong solutions. And then x2 is the same as, so x2 also, if you want, you can extract the whole of this line and then you divide. If you don't want, you can just do directly. So it will be minus 3.09, right? And then minus 4.01 multiplied by negative 0.4278, and then plus 1.12 multiplied by x3, which is 5.11, and then we divide by what? We divide by 10. So what is x2? So you can give me x2. And I asked you to make a program of doing all this. That was assignment 1. And then you test it on an example of your choice. And as I told you that when you make this program, when you program something, start with a simple example. I don't recommend you to start with this 3x3 example. No. I recommend you to start with a simple example, like when I gave you just two equations, and then you solve, and then you can generalize. You can even now go to 20. And once you make your program such that it's able to give you warnings where you have many solutions, you have whatever, then you don't care. You can just wake up from nowhere and give it any matrix, and then you know that if it has no solution, it will give you a warning. that, sorry, there's no solution, you have to do this. Sorry, there are many solutions, it is. So you make a simple program and you keep improving it. You keep adding things one by one, slowly. That's how you make a program. Don't start so complex, start simple. And then you start making it complex, and increasing complexity as you move along. Is that clear? So we have looked at Gaussian elimination method. We have seen that since it's sensitive to round of errors, you can do pivoting. In most applicable cases, we do partial pivoting. Full pivoting, rarely, but I can still ask you an exam, just a simple example where you do full pivoting, just to understand it. But most in practical cases, they do partial pivoting. And so that's what is done. So one application of Gaussian elimination is finding the determinant of a matrix. So I can write here determinant by
Excuse me, sir.
in the chat.
yeah. Yeah. Uh-huh. No, this one I had said just work out to 4 significant figures. In the exam, if you have such a question, I will specify. Okay. Okay. You know, mostly when I'm in front of the screen, I don't see the charts unless I see something, then I can check. Will the sign of the element matter in determining the largest entry in the matrix? No. No. So we look at, that's why I said you check element with the largest magnitude. So you consider the magnitude, you don't consider the sign. Even for this matrix, even if negative 10, even if this 10 was minus 10, then still it will be the element with the largest magnitude. So still it becomes the pivot. I think that one answers the question.
Yeah, sure.
Yeah. And as you are doing numerical, I think most of you are engineering. What you do, even after whatever engineering you are doing, whichever application you do, there are so many because you will be dealing more with the real world scenarios, which are not so accurate. So there are so many errors. You want to minimize errors. And whatever, if you want to find something accurate, for example, 2 decimal places, then your working should be to 3 decimal places. In short, if you want to determine your answer correct to 4 significant figures or m significant figures or m whatever, then you should work to at least m plus 1, so that when you round off, you come back to m. If you do your calculations to the same significant figures, then you might get a wrong solution. So for this one, if we wanted, for example, our solution to be accurate for significant figures, then you need to work to 5 significant figures or more. So that's a note you have to take, that if you want solution to correct to m, specification of m decimal places, m significant figures, whatever, then you should work to at least m plus 1. So we go to one application of Gaussian elimination method, which is finding the determinant of a matrix. And this method is so critical in finding the determinants of largest systems. But before that one, have you ever found the determinant of a 3 by 3 matrix anywhere? Or did you learn somewhere how to find determinants of matrices? Which method did you use? Cramer's, okay. Cramer's rule is also used to determine determinant. Which one is Cramer's rule? How do you use Cramer's rule? I don't know that one.
No, it's not grammars. It's
Is
Cofactors.
I don't really know the name, but there are specific. It involves reducing it into a 2 by 2 and then multiplying it by the elements that are the coefficients of.
Okay, yeah.
Yeah.
So so it's called the cofactor. So one way of finding the determinant of a matrix is just by cofactor expansion, either along the rows or along the column, whichever column of you are choosing. And so that method, because if you have a 2 by 2 matrix, you already have one 2 by 2 matrix, you can evaluate the determinant easily, which you know. If you have a 3 by 3 matrix, a 3 by 3 matrix, then you will get 3 2 by 2 matrices. If you have a 4 by 4, so it means your determinant is increasing very fast. You are having so many 2 by 2 matrices, and that method is kind of tedious if you have a larger matrix. And so that's now where we bring in now this determined by Gaussian elimination method. And so maybe I can first of all just review the previous method that you looked at. That by saying that one way of evaluating the determinant of a matrix, of a square matrix, so I just written, but it's supposed to be a square matrix, is by cofactor expansion along the rows or columns. So I'm thinking, because I'm thinking some of I want to try to get somebody to teach my students, so in Chiromo, about just basically like introducing them to Python, just some few things about Python, and that one will be done over the weekend. So if there is any one of you who is interested, then you can let me know. Then I can also, whenever they want to learn, I can send you the link, so you can learn this. Some of these things I do here, I may do them using, or I do them interchangeably. I can use MATLAB, I can use Python, so whichever. But so Python is more friendly to those who cannot access MATLAB license, because you don't require license. So if you are interested, you can just do some Google, you install Python, and then that person will basically introduce you to, but some of you know, but because so she wants just to introduce some basic things, how to define a string, a scalar, the vectors, and what, and some simple operations, such that when we start discussing some of these programs, then you have an idea. At least you have some basics. I wanted us to cover at least a bit of much of the work before you can start implementing some of the what we have done before. But also, I will just be writing some of them as assignments. You try to implement them, and then we'll go through, discuss. We'll go through at some point. Even also, I can even involve. Do you want to do this in group work? What do you say? What do you suggest? Huh?
Yes, group work will be best because in school, rather in the field, we're supposed to
Yeah.
be collaborating in a team. So it's best if we learn how to collaborate earlier.
But do you guys, can you use Excel to split your names into groups of how many people do you want per group? 3, 4, or 5? And this will
A
count
group of
to
3 will be fine.
half of your cut marks. This assignments I give you about programming, and even the programming classes will also count for your assignment and cut. So they'll contribute to your cut marks. Just even the attendance only. And so what you can do is, who knows how to split just names randomly into groups?
Lennox can do that. Lennox or Joel.
Oh, Linux is an expert. Where is Linux? Oh, so you can do this, right? So I want the class rep sends you the, because I don't want to choose groups. I don't want to give you your friends, and I don't want to use any criteria to choose the groups. I want it to be random, and then so the groups will be ranged to 3 to 5, maximum 5, minimum 3. So you get the class list, and then you split it into different groups of 3 to 5 individuals randomly. Okay, you can write to me after the class. You have my number, right? Na niliandika hapa kwa screen. Kwani siku ya kwanza ulikuwa wapi kwa class? Kuna hapa kuna the two class reps. Niliandika hapa namba. Hao jamaa wako nayo, hata wengine pia wako nayo, watakupatia. So they are, and then you write to me, then I tell you so what to do, and then so you will now be doing these programming classes in groups. It's also good to you learn from your friend how they program. You know you are moving outside the field, and for those of you who are interested, you may need some of these skills outside in the field. So where you go to, whether if it's further studies. And once you develop this art of programming, you start visualizing things in programming skills. Then you can easily switch different languages you want to use. Even if you want to do computing in MATLAB, you want to do whatever, you can easily switch around and use anyone that you want. Okay, so that's sorted. Will account for, out of 30, 15 marks will come from all the assignments, the group assignments. Some of the practical lessons we'll be doing about programming. In fact, I'll keep 5 marks pending. My cut will be this way. So out of 30, let me just write it here so that you note it down. Out of 30, I'll make 10 in class cut. So the sitting cut, whichever you do some, and this will be sitting. And then 15 marks will be group work. So all these group works, you attend all these assignments, programmings, whichever I mention as group work. And then 5 marks will be presentation. Some of you will be, I can just come to class and then I ask one of you to just explain, or a particular group to explain. And whatever you contribute in the groups, that becomes the group marks. But there should be participation. If there is any group member who is not participating, just when you submit assignments, you just put star in the person who is not participating. And then the marks you get in the groups, they don't get those marks. So basically, this will be here and then easy. So if you are doing something good, then it means you should be out of 20, you should be somewhere 18. So so this is what I'll do. So in case of anything, class repachukua atanikumbusha, but I have this thing. So this will be the card. And so I was saying, so one way of finding the determinant of a matrix is just by cofactor
Excuse me,
expansion.
sir. Yeah, concerning the last program you gave us, there's a small program I have. I wished to, in the last 5 minutes of the class, to show it to you, and maybe you can tell me if it does what you wanted it to do.
Did it give you the answers? That's the starting point.
Yes, it does.
Yeah, kama nikupatia inaweza kuwa. Just we make these programs in different ways. Is it in MATLAB or Python? Or which one?
It's in MATLAB. It's in MATLAB.
Oh, okay, yeah, we can look at it after in the last 5 minutes. So we said we have to finish 10 minutes before, right, for your class.
Yeah,
right?
yeah.
So
Sure.
so at 20, that will be 23, 30, 30 or 35. Then you let me know. So 23, 35. So that's meaning we need remaining 25 minutes too, so that we can look at your program in 5 to 15 minutes, and then people can leave for the other class. So if you are given a matrix A, then determinant of a matrix A is given by what is just the cofactor expansion. So is Aij multiplied by Aij. And so where you are just summing up what? So j is equal to 1 until n, and then I fixed. So you can do this along the row or along the column, or still somebody can say I is equal to 1 until n Aij and then Aij. Basically, you can do cofactor expansion along the columns or along the row, and any row of your choice and any column of your choice. Where what I'm calling this capital AI, they are called the cofactors of an element. So to illustrate this, let me define first of all what we mean by these values. So I'll first start by defining what we call the minor of a matrix, no, minor of an element. So, and then we can say that the minor of an element Aij of a matrix is the determinant obtained by deleting the I row and jth column. So if you have a matrix and then we want to find, and they are denoted what? It is denoted M, I, J. So let me just give just a matrix. Suppose a matrix A is given by 1, 3, 4, 2, 1, 1, 5, 6, 7, right? And so, for example, somebody asks, what is M1, 2? That means is the minor. So this is just equivalent to what? Is the minor of an element belonging to the first row and second column. Which is that element? Which element belongs to the first row and second column?
3.
3.
Yeah.
Yeah, 3. Correct. So we say that the minor M12 is the determinant obtained by deleting the row and column containing 3. And so you basically delete the row and delete this one. And so this minor will be the same as what is the determinant. In fact, so it will be determinant obtained. So it is 2, 1, and then 5, 5, 7. And this gives us what? 9, right? So that will give us 9. And so having defined what a minor is, can you define what a cofactor? And then we can say, just also defining that the cofactor of an element Aij is denoted Aij is the signed minor. So if you give a minor to a sign, then you call it the cofactor. So basically, cofactor Aij is the same as what? -1 I plus j, and then mij. So you are giving those elements the sign. So for example, what is A12? It will be -1 raised to power 1 plus 2, and then mij we got is 9. And so that gives us -9. So have you seen the difference of this, right? So you just know the minor, the cofactor is just the signed minor. When you assign this to minor. And so can you, so just example, find the determinant of the matrix above by cofactor method. Let me just rewrite the matrix is 1, 3, 4, 2, 1, 1, 5, 6, 7. Is 1, 3, 4, 2, 1, 1, and then 5, 6, 7. So that is 5, 6, 7. So I said you can apply the cofactor method on each element. No, whichever column of you are choosing, you can choose whichever column you want, whichever row. This method applies to any column or any row. You get the same. So can you suggest which column do you want us to take, or which row do you want us to take?
The first
You
row.
want which one?
First column.
First column. So I will go by this. So that's the first column. And so by first column, it means that the determinant of A will be A11 multiplied by A11 plus A21 multiplied by A21 plus A31 multiplied by A31. You take each element, multiply by its cofactor, and then you sum up along that column. But if anybody wants to try, pick any column you want, pick any row you want, and then you test it. You find that you get the same solution. So we know that A11 is 1, right? So what is A11? So capital A11 is the same as, is a sign minor, -1, 1 plus 1, and then into determinant of the matrix obtained by deleting the first row and first column. So we get this is 1, 1, and then 6, 7. And also these things you can do them in your head. So if you can do, even you can skip these steps, it's okay. You can just keep them. So that is 6 minus 7 minus 6, that is 1. So that gives us 1, right? Confirm that it's 1. And then A21, what is A21? A21 is 2. Now A21 is -1 raised to power 2 plus 1, and then determinant of matrix obtained by deleting the second row and first column. So it is 3, 4, 6, 7. 6, 7. That's 21 minus 24. We get -3. And then negative here, so that is positive 3. And then lastly, we know that A31 is 5. Now what is A31? Is -1 I plus j. So 3 plus 1 into the determinant of matrix obtained by deleting the third row and first column. So it will be 3, 4, 1, 1. So that is 3, 4, 1, 1. So that gives us -1, and this is -1, correct? So we said that now the determinant of A is the same as you multiply each element, multiply by 1, and then plus 2, multiply by 3, plus 5, multiply by -1. And that gives us 6, 7, we get 2. Is it correct? Is it? Did we make a mistake anyway?
Correct.
Yeah. And so even if you have 10 by 10, then that's why it is tedious. Because assuming it's just defining the cofactors. Assuming you are finding you have this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 1, 2, 3, 4, 5, 6. And then one, 2, 3, 4, 1, 2, 3, 4, 5, 6. So assuming, for example, you have this, and somebody tells you to find, for example, find A 4, 5. It means you find the cofactor of an element belonging to the 4th row and 5th column. So 4th row 1, 2, 3, 4. That's 4th row, and 5th column 1, 2, 3, 4, 5. So it's basically element number 11. And we said that the cofactor of an element is just the signed minus. So it's -1 raised to power 4 plus 5. And then the determinant obtained by deleting the ith row and jth column. So it means I will delete this and I delete this. And so what happens? We now remind that to find the cofactor A45, you need to evaluate the 5th determinant of 5 matrix. So that means you need to go through the same process. So I'll have this is, for example, 1, 2, 3, 4, and then 6, and then 7, 8, 9, 6. Oh, 9, 6, 7. I skipped some values. 1, 2, 3. Okay, I skipped something, 2, and then 7. But so the point I'm trying to make is that to find the cofactor of that 11, you need to evaluate a determinant of a 5 by 5 matrix. That means now for you to find the determinant of a 5 by 5 matrix, you need again to follow the same procedure, such that you identify the cofactor of each element along the row, and you now evaluate again the determinant of 4 by 4 matrices. So it means you will need, if you are going along this row, you will need first of all 5 determinants, 5 determinants of 5 by 5 matrices, because each of these will give you determinant of 5 by 5 matrix. And then in each determinant of a 5 by 5 matrix along any row, you need 4 times determinants of 4 by 4 matrices. And if you go to a 4 by 4 matrix, you need again 3 times determinant of a 3 by 3 matrices, and then for it to 2. So even doing only cofactor of one element, you have gone through a lot of procedures, so many procedures, which is complex. And so that's where now this Gaussian elimination method comes in. And so we need just to write the properties. So we use Gaussian elimination method based on the following properties. So I was just giving you this example so that you appreciate why this method will be important and why, because here it simplifies what we will have done here. If you check maybe 2 by 2, you might think, this Gaussian elimination method is not even important because maybe they seem to have the same in terms of expression with both of them are the same. But if you, as the matrix increases in terms of order, now the Gaussian elimination method gains an advantage over the cofactor expansion. And so, which properties that when you do this method, you have to take into account all these properties. That one, if a scalar multiple of one row of a matrix is added to another row, then in terms of a matrix remains unchanged. The things I was mentioning in the first class, that if a scalar multiple of one row is added another row, then the determinant remains unchanged. So basically, I was mentioning this in a different way, that the row you are eliminating should not be multiplied by any number. And if you happen to multiply, then know that the same will multiply the determinant. So in the end, you have to divide it so that you get the accurate determinant. You have to reverse back. Then two, if any two rows or columns are interchanged, then the determinant changes sign. So if you obtain a matrix, for example, B from a matrix A by swapping rows or swapping columns, then the determinant changes by negatives, multiplied by a negative. Three, if a matrix B is obtained from A by multiplying one row of A by a scalar, say alpha, then determinant of B is the same as what? Alpha, determinant of A. So if you multiply any element by a scalar, if you multiply any row, you multiply either row or column, whichever. If you multiply a row by a number or multiply a column by a number, then the determinant will also multiply. That number will multiply the determinant. 4, if B is obtained from A by, say that B is the same as, just multiply the whole of matrix A by a number, for example, alpha. Then determinant of B is the same as alpha to power n, then determinant of A. If, remember here, A is of order n by n. So if you multiply the whole matrix by that number alpha, then determinant of B will be alpha to power n, where n is the number of rows of A. And then the most important about this Gaussian elimination method, 5, that if you have a triangular matrix, then the determinant of a triangular matrix is obtained by just the products of the main diagonal. If A is a triangular matrix, then determinant of A is the same as what? A11, A22, A33 until ANN. You simply multiply that, just the elements along that one, along the main diagonal, and that's basically what it does. So basically what you are doing is you are reducing the matrix into a triangular matrix. And then once you get a triangular matrix, you multiply them by you multiply the elements along the main diagonal. So let us do an example, and maybe I can start with the example we just did, the first example, the smaller one. Can you read for me the example we did? This 1, 2, 3, and then one for whatever. So the matrix is 1, 2, 3, and then 5, 6, 7. So if you want to find the determinant of this, you can simply follow the method we did when you solve the system. Or you can multiply anything, provided you keep track of, if you multiply any element by whatever, then you keep track. So this determinant of A, when I write straight lines, they mean determinant. So 1, 2, 3, and then 2, 1, 1, 5, 6, 7. So this is row 1, this is row 2, this is row 3. I told you that this, if you want, you can put them. If you don't want, you leave it. So I'm keeping row 1 unchanged. 2, 3, that's just row 1. And then I want to make this 0. I can multiply, I can find the scale factors as we did the scale factors. And then I multiply by the scale factors. Or if you don't want, you do something, but you keep track of these determinants. And so if we do this, then I can say what? I can say that my new row 2 is the same as row 2 minus 2 row 1, right? In fact, yeah, that's still the scale factor. So minus 2 row 1. And so I'll have this is 0. And then this is minus 3, right? Just confirm. That's minus 5.
Yes.
And then here I'll have, so that is row 3 minus 5 row 1. And so that is 0. That's minus 4, right? And then that's 15. That's minus 8. Is it? And so remember that what we said, since I'm eliminating row 2 and row 3 and I've not multiplied by them by anything, determinant has not changed any. So I can still take the negative outside, and then I say that determinant of A is the same as what? Negative 1, and then I can say 1, 2, 3, 0, 3, 5, and then 0, 4, 8. So what I said that if I can factor out this out, and then to remove by the determinant, I can also factor out the negative here. Huh? No, something is amiss somewhere. Oh yeah. Since any number I factor out will be multiplied by that determinant, so it's still okay. I can multiply the determinant, that number. And then now I also want to eliminate this. So just keep track of this. Just keep track of any factors you keep out. You keep track of them. And so row 1 has not changed. 1, 2, 3. Row 2 is not changing. 3, 5. And then row 3, what's happened to row 3? I can say it is what? 4 row 3 minus 3 row 2. And so here, since I've multiplied row 2, no, row 3 by 4, it means in the end, I'll have to divide it by 4 when I find the determinant of A. So basically what we have done here is, so if we do this, then I'll get here a 0 here. Here I'll get a 0. And then so 4, that is 32 minus 15. Huh? I think something is missed somewhere, right? It was supposed to be 3. Row 3 minus 4 row 2. Yeah. So I multiply this by 10, multiply this by 4. I want to make them 0. So 0, 0. And then so this is 3 minus this is 24. Minus 15 is, no, minus 20. That's 4. And so I've gotten a triangular matrix U whose determinant is what? Is 1, 2, 3. And then 0, 3, 5, and 0, 0, 4. Did we make a mistake in the first determinant? Because I'm getting something different.
You used a different first row.
I used a different first row. Okay. Oh, I was wondering why was it bringing something different. I wanted to use the same first row so that you get the same one, but so no problem. Yeah. So here, what the determinant of U? I said that since we have a triangular matrix, determinant is the same as what? 1 multiplied by 3 multiplied by 4, right? Which is 12. And so the question is, now what's the determinant of A? Can you tell me what's the determinant of A? So the only thing you have to keep track of determinant of A is this factor here. Since I multiplied the element the row I was eliminating by a number, that number is embedded in the determinant. So it means the determinant of A will be 12 divided by 3. If you happen to multiply by a number obtaining a new matrix, then the original matrix will be, you divide by the same number you multiplied with. And so this gives us 4. That's the determinant of this matrix. But we can see, let's try, let us see directly. That is 1. I have 7 minus 6, that is 1. That's negative 2. So minus 2 into minus 5. What's 14 minus 5? That's 9, right? And then plus 3. That is 12 minus 5. 12 minus 5 is 7. So that's 1 minus 18 plus 21. That's 22, which is 4. And we get the same one. So just keep note of that property. The key property where most people make a mistake is this part. If you happen to do a row reduction and you happen to multiply the row you are eliminating by anything, then for you to get the original determinant, you have to divide by whatever you multiplied with. Even here, when I obtained this new matrix here, for me to move this to a positive value, I multiplied the determinant by 3. No, by negative, for this to be positive. And then I also multiply this by negative for them to be positive. So in the end, I should divide I should divide by the same values I multiply by -1, -1. So that's the key thing that makes people fail. When solving the system, you don't care about these things anymore. You don't care about them. But if you are solving the determinant, you have to care about them and you have to keep track of them. Also, if you want, can you even do this same thing even when you construct in your program make it such that it calculates the determinant of a matrix. So you are just building your own program so long as you go. You remember you made the program, you are having a matrix, the program reduces it into row echelon form. After reducing it, it solves the system. After solving, you can also get the determinant. I know these things, in most of these, like if you go to MATLAB and just write determinant, it will give you the determinant. But so I'm trying to make you understand what happens in the somebody who made that whatever is happening that when you put it, you are calling some function. How does that function work? That's basically what we are doing. So you are trying to develop your own function that you can use. Even if you don't know, then you at least you know what is happening in the background. And remember, this only works if A is square. For you to do row echelon form, you are doing it, remember, on the augmented system. And so what you can do is once you do the row echelon form, you can now tell your program to take the first part and leave the last column. And then in the first part, it now considers it and finds the determinant. And also you make it, if A is not a square, then it also make a program so that it gives you a warning that, sorry, your matrix is not a square, I cannot find the determinant. So it outputs a warning. But so basically, that's what you can do. The example you can go and try at home is -1, 3, 5, 2. Then I have 1, 9, 8, 4, 2, 1, 1, -1, and then I have 0, 1, 0, 1. You find that determinant. Just use this Gaussian elimination method. And later on, if you want one, when you make your program, you still test it and then see that do you get the same solution or do you get the same answer? Remember, the key thing is getting the right solution, understanding what's happened before you even make a program. Any question?
Yeah, I have a question. Where you've multiplied the matrix with -1 times -1, could you explain how it came about? Where you've multiplied when we are doing the operations, you multiplied -1 times -1, then the operation. Yeah, here.
Yeah, so I wanted to eliminate these negatives. And so to eliminate this negative, I can factor out -1, right?
Yes.
Yeah, so it means I can basically multiply row 2 by -1, right?
Yes.
And then I can multiply row 3 by -1.
Okay, yeah.
And then it comes to this property I told you, this property number 3, that if you multiply any row or a column by a number, a scalar, that number also multiplies the determinant. Right?
Yeah.
Yeah. So in fact, I should have written this in opposite way and say that since I multiply this, then it means -1 squared that A is the same as whatever you have here, right? And then since I multiply this by 3, this matrix, then I have -1 squared multiplied by 3, determinant of A, the same as determinant of U, which is 12. And then to get the determinant of A, you now divide by these values. So it's just, I did the same principle. I multiply by scalar, but that scalar is -1.
Yeah, thank you.
Yeah, so that's the critical rule that most cases you will encounter in most things. And if you make a mistake, most people will make a mistake in this rule. Some of these, like the interchanging and whatever, most people will keep track of this. Any other question? So we can give a chance somebody wanted to show us the program, unless somebody has a question. Uh-huh. Uh-huh. Okay, and there's a statement I was making. No, so there are two rules here. Rule number 1, right? And rule number 3. And they end up confusing. Rule number 1 says, if a scalar multiple of one row is added to another row, then determinant remains unchanged, right? So if a scalar multiple of row 2 is added to row 3, then determinant remains unchanged. So it only changes if you multiply the row you are eliminating. I'm just using here row 2 to eliminate row 3. And so this factor which is here has not been affected anywhere on this row 3. It's only just as a number to eliminate. So row property number 1 and property number 3. If a scalar multiple of one row is added to another row, the determinant remains unchanged, so it does not change. And then 3, if you multiply by a number, then that multiply the determinant. So in short, the number which affects is the number you multiply with the row you are eliminating. That's the summary, right? But if you follow the same Gaussian elimination method used in eliminating, then some of these things are not coming. I just avoided it because of avoiding fractions, but you can go through the same Gaussian elimination method by looking at the scale factors, lambda 2, 1, lambda 3, 1, and then you multiply and then you eliminate. Those things will take care of these things you are looking at here, these properties. They are taken care of automatically. And then you don't have to worry about anything unless you are interchanging the rows only. Any other question? Or maybe we can do this. The ones who wants to show the program, I can give you on Tuesday. We can have a class on Tuesday, and then we can discuss a bit of some of these programs, right? No, but if you want to show, I'm okay now. You can show me now. And also the others, if they want to see, they are free to remain. Otherwise, if somebody is rushing to class, then you are also free to go to class, and then I can remain with the one for the program. That's okay.
Yes, it's okay.
So in the next class, we will look at Gaussian Jordan elimination method. And maybe I just go to its application part of it, but you have to find the universe. So I can stop sharing and then you share your screen, right?
Yes, sure.
Yeah. And for those making the program, if you want, you can first of all by start making a script. Just you put everything in the script, and then later on, if it works, then you convert that script to a function, so that you only work you need is just separate the matrix, and function does the rest. So I'm stopping sharing. So you can now share your screen. I said the rest you are free to leave if you are going to class. For those who want to see the program, you are free to remain.
Yes, I hope you can hear me and see the screen.
Yeah, sure. Yeah.
Okay, so thank you very much, sir. Here's the MATLAB script for solving a system of linear equations. So I'll briefly explain each line. Here we are inputting the number of equations and storing it in an integer. Yeah, here we are initializing. A is for initializing the matrix by appending zeros. B is the constant vector that we usually augment to the matrix, the solutions. And then here is a for loop, nested for loop for iterating through the matrix and the column vector for the user to input the specific values for each coefficient. And remember, we were
So
told
it
that
asks the user
for
to input, right? Yeah.
yes. And
Okay.
remember, matrix it starts from 1, row 1, 2, 3, 4. This code basically it iterates through the rows from I to the nth row, and then J
You put the numerical string. Okay. Yeah. So you are muted. Are you?
okay, I'm sorry. I hope you can hear me.
Okay. Yeah.
Convert this integer to a string so that you can append it to this
Okay.
string
Yeah.
because you're working with those are two different data types. Then here you prompt the user to input the constant terms that we will use to augment the matrix. And then here, remember from our last class, we saw that if determinant is 0, there might not be a build function with the determinant of the mixed solution. Otherwise, we'll solve.
So first of all, this is correct, right? But so what I want you to check,
Yes.
Assume you
Yes.
don't know the determinant, right? And then you do what I told you. You check that only when you after reducing and you check the last row.
Yes.
So just reduce it and then check the last row. If it has rows, then you check those 6, right?
Yes, sure.
Yeah. But it's also correct.
Yeah. And then now we solve using this backslash operator, which will solve the system of linear equations for us and store the solution in this x, which will be a vector, and then we display it. Okay, so if I just run it, sorry. Okay, so using the last question, maybe someone can remind me the last system of linear equations that we solved. There were 3 questions.
I can give you any. Just say
put,
there are 3.
yeah, 3, and then 2.11. That's A11. Notice now which adds the 1. That's sorry. We do 2.11. And then the next one is minus 4.21, and then 0.921. And then now B1 is the constant term, 2.01. Then now the second row, 4.01. Then we have 10.2. Then we have minus 1.12. and then minus 3.09, and then we have A311.09, and then 0.987, and 0.832, and then 4.21. And I will just give you the solutions.
I'll get the solutions. In fact, they're the same ones we got, right?
Yes.
Yeah, 5.11. Yeah. So basically, your program is correct, right? But so the things you change, that
Yes.
line, what you did on line 27,
Yeah. 19.7.
yeah, it's basically when you divide this is using Gaussian elimination method, and you divide that on the back division, right?
Yeah.
But so I wanted you to do that yourself. Basically, you are trying to reproduce what happens behind the scenes, because you know when you just write x is equal to a slash b, basically it's taking your system, reducing a into a Gaussian elimination method, something like that one, and then multiplies b. It finds them. So you are
Yes.
finding, in fact, you are finding the augmented matrix. So I wanted you to try to go through that process yourself. Basically, make another loop, right? That you
Yeah.
take A1 and you identify the pivot and then reduce whatever is below, you keep reducing. Loop through S rows and columns again. So I'm just leading you to understanding what happens behind the scenes. And
Yeah.
the
Yeah.
practical sense,
Sure.
this function, I want you to try to replace that function. But this is correct, it's working correctly. And I like that you are
Thank.
checking whatever it is determined is equal to 0. So next class,
Yeah.
I will
Thank you.
also share the program I have, and also maybe somebody can hear. We can discuss this maybe until then. Let me hope you make the group by Friday, and then on Monday I can see a group that which will be willing to present on Tuesday. So all groups will
Yes.
present.
Thank you.
So next week on Tuesday we can have 2 groups which will be ready, and then after next week on Tuesday I will just assign them randomly the groups to present. But next week if the groups are ready, they can tell me those are ready. Then I can give them a chance. Any other question? If no further questions, then we can call it a day, and we meet next week.